It's the most common form of public transportation there is, the elevator. All over the world, elevators carry riders of every age, and passengers assume their ride will be a safe one. In fact, thanks to strict and ever-changing codes as well as many devices designed to protect passengers, elevators are the safest form of transportation in the world today. Since the early 1850s, elevators have been equipped with a car safety to prevent the elevator from free-falling in the event of a hoist rope break. An added benefit of this safety will also prevent the car from overspeeding in the down direction. But if the elevator car is not fully loaded, it usually weighs less than the counterweight, and in case of a malfunction, will actually fall up. In fact, it's more common for an elevator to fall up than down, and may actually leave the floor with the doors open. Until recent years, devices to protect against these potential catastrophes were relatively unheard of. Many articles and discussions have targeted the need for protection against injuries caused by cars leaving the floor with the doors open and overspeeding in the up direction. Today, safety codes in Canada and Europe, and soon in the United States, require that all elevators in new construction be equipped with an emergency brake system that will prevent overspeeds in the up direction and some to stop the car when it leaves the floor with the doors open. Several tragic accidents have happened due to these types of occurrences. So, it would seem extremely prudent for safety-conscious building owners and contractors to employ such a device on any elevator, whether a new or existing installation. Several devices have been developed in the hopes of preventing such accidents. One of them is the traction shiv brake. This device employs a frictional plate located underneath the traction shiv. When the car overspeeds in the up direction, or if the car leaves the floor with the doors open, the frictional plate comes in contact with the traction shiv and is then pushed sideways in the direction of travel. This causes a wedging action, applying a braking force to the traction shiv, stopping the shiv. Another device is the bidirectional safety. The down direction safety is activated, as it always has been, by the governor. When activated, the safety jaws clamp the rails, stopping the downward motion of the car. Designed to stop the car in the event of free fall, this action must be stronger than the up direction. The governor design for the bidirectional safety will also activate the up direction safety, which consists of a separate set of jaws. If the car would leave the floor with the doors open, the governor is held in place, allowing the governor rope to set the safety in the proper direction, with the jaws clamping the rail, stopping the car. A third option is a rope brake. In the event of an overspeed or car leaving the floor with the doors open, a rope brake would grab the ropes and stop the car. At Hollister Whitney Elevator Corporation, along with our sister company, GAL Manufacturing in New York, we've created a reliable, inexpensive emergency rope brake system called the Rope Gripper. Our primary objective was to design an emergency rope brake system that would operate under all conditions, eliminating the danger of slipping traction. In addition, a rope brake would not cause any undue stress on the machine, and being located in the machine room, would be totally accessible and could be conveniently tested on numerous occasions. Since the rope brake could set or reset without movement of the car, we could apply it during a power failure and have it automatically reset when power was restored, not requiring a technician to be called to the site to reset. This eliminates the need for battery backups, but would also require a technician to reset the brake if there was an actual emergency overspeed or if the car left the floor with the doors open, to determine the reason for the gripper to activate. During the development of the rope gripper, the Hollister Whitney GAL team worked to anticipate a wide range of situations that would not only meet current safety standards, but also accommodate future safety requirements and conditions, such as how a braking system would operate in the event of a power failure. The rope gripper will grab the suspension ropes to stop the elevator in the event of numerous failure conditions, including overspeeding in either direction, or when the elevator leaves the floor with the doors open. The rope gripper employs springs, a rotating shaft, and a stationary cam to obtain a mechanical advantage and apply a constant and equal pressure to the elevator suspension ropes. The cam action causes a changing mechanical advantage and is designed to compensate for any lining wear. providing a constant force on the elevator ropes even with the springs extended to less than half their original compressed value. An electric solenoid operates a trigger that prevents the springs from extending when the rope gripper is in the loaded, open operating position. But when the power source is cut due to electrical or mechanical malfunction, the springs will extend and the rope gripper is deployed. One brake shoe moves toward a stationary shoe which clamps the suspension ropes and brings the elevator to a smooth, safe stop. The brake shoes are designed with a lining material that prevents any damage from occurring to the ropes, but will still withstand many operations of the gripper. As the springs extend, oil is forced from a cylinder into a tank, which allows for a smooth, shock-absorbing type action. In order to release the gripper's hold on the elevator ropes, this hydraulic pumping unit is used. Oil is pumped into a cylinder, which extends a plunger that compresses the springs attached to a movable shaft, which then moves down the cam against the trigger. The rope gripper is now set and ready to deploy in case of an emergency. Watch the rope gripper in actual operation. Notice that the gripper shoes are open and the switch is closed, indicating to the elevator controller that the elevator can run up and down freely. If an overspeed condition exists, the governor overspeed switch will open, indicating an emergency condition. The power supply to the gripper is disconnected. This de-energizes the electrical trigger solenoid and releases the gripper. A switch on the gripper then opens, signaling the elevator controller to disconnect the power to the motor and brake circuits. The elevator car is brought to a smooth and safe stop when the gripper shoes close. When the overspeed switch is reset, the gripper power supply is established, and the gripper automatically returns from the activated to the loaded position. The contact then opens and disconnects the hydraulic pump. Upon reaching the loaded position, a switch closes, allowing the elevator to run. If the elevator leaves the floor with the doors open, contacts on the elevator controls will indicate an emergency condition, and the power supply to the gripper is disconnected. This de-energizes the electrical trigger solenoid and activates the gripper. If an overspeed condition activated the gripper, or the doors were open while leaving the floor, this indicates a problem with the elevator. In this case, reset will not be automatic. A technician would be required to investigate and correct the problem. If the gripper were activated by a power failure, it would immediately deploy. When power is restored, the gripper automatically resets itself.